Yeah, thank you. It's really wonderful to be here, right? And see the variety of non-local systems and how they have developed over the last 15, 20 years. So I will talk about kind of a subject that I got interested over the last maybe 3-4 years. And I will mostly show you kind of a lot of problems that exist in the area and not so many answers that we have. But kind of I really see this more as a starter of a discussion. And if you want to discuss some of the problems, I'm kind of happy to. So what we'll do is motivated by the problem of sampling. So, sampling typically high-dimensional measures is a very important problem in applied sciences. Kind of sampling potentials for, kind of in chemistry and so on, right, is letting us learn about molecules. Whenever you have a Bayesian inference problem, right, you're sampling a posterior distribution. So, there is a large industry actually in applied sciences of sampling measures in high dimensions. Now, we don't really have something to contribute in terms of yet effective algorithms yet that do that, but I want to add, kind of advance and advertise kind of a potentially different point of view. And okay, this is going to, in that sense, a receptive audience, because what I would like to look at is interacting particle-based samplers. So what are the kind of somehow workhorses for sampling nowadays? These are, Markov chain Monte Carlo, Hamiltonian Monte Carlo, and similar approaches where there is a random process whose invariant measure is the target measure, and you are executing that process typically in parallel. And your goal is to generate an IID sample of a given measure, right? So the best, kind of outcome is that you generate IID samples, and this independence, kind of is often useful kind of also for downstream tasks. But very often downstream tasks are really computing averages of quantities or integrals of quantities that one is interested in. And if that is the task, well, then I'm thinking, well, maybe if we have a random sample, maybe if we have an ordered system of particles, right? So this, they are not independent, but maybe they, in totality, approximate the target measure better than the IID samples would, and in that sense, they may even be more advantageous for downstream tasks. So kind of I have two lines, right? So one is that interaction may be useful for sampling as such, but the other is that interaction provides us with a different outcome, namely provides us with something like this instead of something like this. So, okay, to be able to, say something maybe a little bit mathematically, kind of what do we mean by this? Well, first of all, when I said it approximates the target measure better, I have to discuss a little bit in what sense. How am I measuring how close to the target measure we are? So, we need some metrics on the spaces of measures. So, of course, one that many of us are familiar with is transportation metrics, and in particular the Wasserstein metrics. But then I'll mention others like the maximum mean discrepancy or kernelized Stein divergence, and perhaps some others down the way. But okay, in terms of comparing these two pictures, right? This is what I would like to do. So first, if I have a target measure, let's call it mu, and I would like to approximate it by particles. So as a measure, I consider particles via this empirical mean, and then my goal really is right. So maybe my goal really is to measure the distance between this, particle-based measure and the true measure in some metric d. Now, if we are drawing IIDs or IID random samples, right, then this is somehow what I call a random quantization. So we are looking at the expected distance between the empirical measure of the sample and the true measure measured in this distance d. On the other hand, the optimal quantization error is if we design the points that we are gonna use, and then we look at again the empirical measure that corresponds to them, or just delta masses at these points. And again, I'm using the same distance, but now I'm looking at what is the best that I can approximate the true distribution using particles with respect to this distance d. And this is what I call optimal quantization. So okay, let's do an example. Let's look at the optimal transportation distances. So we want to compare two measures, mu and nu, and we look at transport plans, right, which of course are measures in the product space with first marginal mu and second marginal nu. And then we look at the infimum among all possible transport plans of the transportation cost, and the cost that I'm considering are the p power of the distance, where p is equal to 2 would be the Wasserstein distance, and then to get a metric we raise to power 1 over p. So these are classical results. This is known. So there is this, famous paper by Ajtoj, Komloš, and Tushnadi, right, who designed this dyadic way that enables one to basically prove these results. Their result was not kind of fully written out in d is equal to 2, but let's say the earliest full proof that I know is actually in this paper by Talagrand and Jukic. So basically, okay, we note that, with respect to Wasserstein metric, right, in high dimensions, or, in any dimension bigger than 3, we have that the approximation rate is n to negative 1 over d, which, is what we saw also yesterday, right, and what decays with the dimension, right? So what this is, kind of our approximation ability decays exponentially with dimension. So, or if you want the other way, if I want to approximate, let's say, even just within the distance of 1/2, as the dimension grows higher, I will need a number of points which is exponential in the dimension to achieve, even a very modest approximation error. Okay, so basically, Wasserstein distance is too fine to be able to, be accurately approximated somehow in high dimensions. On the other hand, well, not on the other hand, let us also note that for the transportation distance, the optimal, if I place optimal points rather than random points, we are actually scaling in the same way. The constant in front would be different, but the scaling law is the same. This is very easy to understand. Let's say if you look at a grid in high dimensions and you look at the grid spacing, this would be precisely n to negative 1 over d, and this is what you expect that your transportation distance would need to be. But okay, let's look at some, to introduce some metrics that do make sense in high dimensions. Can we approximate in high dimensions? Okay, I need a little bit of a review slide. So let's say in statistics, reproducing kernel Hilbert spaces are very widely used, but let's say I only learned about them, not that long ago, right? So I did not encounter them in my mathematical education. So reproducing kernel Hilbert spaces are just Hilbert spaces. Let's say here we look at spaces of functions, where the pointwise evaluation is a continuous mapping, right? So, for example, right, if you take a fractional Sobolev space where, okay, you can take this to be integer, but this S is bigger than dimension over 2, then we know that this space is embedding in the space of continuous functions, and thus the pointwise evaluation would be a continuous operator on that space. Now, given that this is a Hilbert space, for any continuous mapping by Riesz representation theorem, there exists a representer function or feature map, right? So which is actually representing the pointwise evaluation as an inner product in that Hilbert space. So okay, so for any point, you have a mapping. You have a function in that Hilbert space such that the inner product with that function is giving you the pointwise evaluation. If I look at the inner products of this, phi x and phi y, the object that we obtain that depends on two variables now is what is called the kernel function. And I know that, if I take any function which is sum of these, feature maps, and I compute its norm in this squared, in this Hilbert space, I really get this sum on the right-hand side. Since the norm is positive, it's always greater or equal than 0. So what this is telling you is that regardless of whether AI, Aj are positive or negative, these sums always have to be greater or equal than 0, or in other words, that this kernel is positive definite. Okay, if I look at the spaces which are translation invariants, right, then this kernel actually can be represented in this form, and I just conclude, right, kind of with noting that the norm in this Hilbert space kind of has the following Fourier representation, right? So if you look at a function f, right, then first positive definite kernel by Bochner theorem, right, are their Fourier transform is positive, right? So this is a real positive function, and basically in the Fourier domain, norm in this reproducing kernel Hilbert space is nothing but a weighted L2 norm. And really this is telling you kind of the decay of this is telling you about the regularity of the functions f. If we are still in the kind of original domain, but I look at functions which are given as a convolution with k, then their norm squared can be represented as this double integral, basically like a non-local interaction. But of course, this measure theta is not required to be a probability measure, right? It is an arbitrary measure. The kind of the most frequently used reproducing kernel spaces are the ones with exponential kernel or the Laplace kernel, although certainly Sobolev is also popular. Now, if you look at the dual to reproducing kernel Hilbert space, and I just look at the dual norm, this is what is called the maximum mean discrepancy, right? So maximum mean discrepancy is nothing else but the kind of the dual norm on this reproducing kernel Hilbert space, and it can also be explicitly characterized by this double integral over here. And okay, so we note, kind of if we think about okay, you have you perhaps want to design a flow towards a measure pi. So think of this as a function of rho. As a function of rho, right? Well, this will have a very familiar form, right? Because this is the non-local interaction energy. This is going to be potential energy, right? And well, this term we actually don't care about. Right, these m, for a wide class of kernels, the maximum discrepancy metrizes narrow convergence of measures. And okay, what are their approximation properties? So this is also known classically, right? Is the kind of again, there is a wide literature, right? But if you look at this, this is actually, if I compare two measures and maybe one of them is discrete, right? Then this is actually the maximum error of Monte Carlo integration over a class of functions. If your class of functions is simple enough in terms of VC dimension, right? So if there were some complexity measures, then you should expect that the error over that class of functions should scale the same way as the error over a single function. And we know that Monte Carlo integration over a single function would have an error of 1 over root n, right? Which is kind of what is behind these type of results. On the other hand, if you look at the optimal points which are designed in an optimal way, so we have this result, and I have to say this is just a proof of concept. We don't have this is not a deep mathematical result that we are presenting here. It relies very much on what is known in quasi-Monte Carlo integration. But again, for smooth enough kernels, basically you have that the optimal quantization error is much better in terms of scaling than the random quantization error. So namely, note that here it's more or less like 1 over n, and here it's 1 over square root of n. By the way, I'm not claiming that 1 over n is optimal. There is strong numerical indication that in low dimensions it is actually off by a power, and also it is not clear even kind of for classical quasi-Monte Carlo integration whether this power is I bet that it's not optimal, but let's say even whether it is needed is somehow not so clear. Okay, so MMD then seems to be a measure where both that we could use it in high dimension, and then that the optimal placement of points would give us somehow better error. By the way, I note that again, because MMD is basically the maximum error that you should expect when using your sample points for computing integrals, so using a Monte Carlo type approximation. So basically, if I get if I approximate a measure with respect to MMD, then I know that my integration error for downstream tasks, at least over such class of functions, would be very well controlled. Okay, so with that, okay, so maybe we want to minimize the maximum mean discrepancy, and then of course, one can look at this energy and look at the gradient flows. And this was actually, first looked at people in the machine learning statistical community. There is somehow a number of other papers, right? So it is not really the mathematical community that somehow noticed this first, although it was sort of out there. So if we look at this, PD, right? So it has this non-local interaction term, and then it has this potential term, right? And then, I'll just make one, remark, mostly for Jose Antonio, right? So, of course, you would recognize this and you would say, well, if I have if I had a potential which is non-local, right, but repulsive attractive, and it is smooth, then you know that the minimizers are not going to be very smooth, right? On the other hand, here, the unique minimizer of this is going to be pi. So if pi is smooth, then, this external potential makes the minimizers, completely smooth. There is, and I'm kind of fascinated by this transition, and we'll see a trace of it coming back later on. Okay, so of course, like as known for non-local interaction, they make sense at the level of particles. So one can write down this energy for particle measures, and again, this ODE system gives us an exact solution of the PDE, and due to the smoothness of the energies involved, right? So this is lambda convex in the Wasserstein sense, and one does have stability kind of on finite time intervals, right? But the question, right? So somehow, okay, we have a unique minimizer, right? But not much is known really about the energy landscapes of these, and kind of do in general, right? Do these flow converge to the global minimizer, and at what rate? It's not going to be exponential, but still, I think that 1 over t is expected, right? But there is no really proof of that. So this is an easy kind of problem to state, but there isn't all that much work actually done. And the other thing is, right? If you look at the particles, right? They will always remain particles, so the particles do not converge such to the global minimizer, but then you look at, well, okay, this is actually, yeah. So what will what can one say about the, if you look at particles, about the distance to the global minimizer as time goes to infinity? There are some positive results. So there is actually a very nice recent result for energies which are do not fall in this kind of class where the Wasserstein gradient flows can be used, but where actually PD techniques are useful. So if one looks at Coulomb potential, right? So this is, well, it doesn't fall actually also in the class of MMDs that I discussed before, right? So the statement that I made before are not entirely true, but do not hold for this kernel, but still the OD and the PD make sense. In that case, right, there is this recent result by Bouffadin and Viellard saying that in that case they have actually exponential convergence to the target distribution, right? But again, in general, these questions are quite open, and what is noticed that in practice, actually, right? So this convergence, especially for smooth potentials, tends to be rather slow. For non-smooth potentials, let's say something that will grow linearly, right? So negative distance, right, seems to give among these potentials maybe the best result. At least, that's what people in community observe. Now, I noticed that in terms of sampling, this is not really a viable strategy, and the reason for that is that to formulate this flow, right? So usually in sampling, right, what do we know about the target measure we want to sample? Usually we know a potential function, and what we would like to sample is the Gibbs distribution, so e to minus u up to some unknown normalizing constant, right? And if I only know the potential, right, then I'm not able to really compute this energy. I'm not, the problem is that I don't know pi. I just know that pi is of the form e to minus u, and let's say this convolution then does not make sense, right? And I can only use this maybe in a generative setting, but not really in a true sampling setting. So, okay, so let's look at some, other approaches, right, which can be used to approximate Gibbs distributions, right? So a lot of those are based on relative entropy or Kullback-Leibler divergence. So we have the target measure pi, right? Of course, this relative entropy is minimized when rho is equal to pi. And let's say if you look at the gradient flow of the Kullback-Leibler divergence with respect to Wasserstein flow, right? In the famous paper, Jordan Kindleator Otto paper, right? They have shown that this gradient flow is nothing but the Fokker-Planck equation. I'll just, kind of very quickly, kind of go through how, one could somehow see that, right? So, for any, gradient flow, right, is the negative gradient vector minimizes the inner product of the vector with itself plus the differential or the first variation in the direction of that vector. So whenever you have a functional and you want to compute the gradient flow, you can, minimize the Rayleigh functional, right? In the same case of the Wasserstein gradient flow, right? In this Lagrangian description of velocities, here we have the kinetic energy, and okay, this is just the first variation of the relative entropy, where again pi is e to minus u up to a constant, right? So pi is e to minus u. And okay, when we minimize Rayleigh function, this is quadratic in v, we obtain that the optimal, the velocity that corresponds to minus gradient is this, so the corresponding gradient flow is given by this equation. And if you like, right, okay, so this is making sense on in the sense that I only need the potential function to be able to write this down. But let's see if I want to do a flow of this equation to compute, for sampling, right? I don't think of this as PD, because if we wanted to solve it as a PD, we would need to discretize the space, and in high dimensions, of course, this is prohibitive, right? Again, you need the number of points to just discretize the space would grow exponentially. So what is done is the most, let's say Langevin dynamics is really just the SD whose mean field equation is the Fokker-Planck equation. And if individual particles are evolving by white noise to obtain the the heat equation plus the potential, right? Then their expected distribution is evolving according to this equation and is converging, right? So in that case, we get, let's say, if U is convex, right, we get exponentially fast convergence, and this is quite viable and works very well in high dimensions. The question is, what if U is not convex, right? What if U is multimodal, has a complex geometry, right? There are, of course, many tricks that one can use, but I would like to go back to kind of my initial point is, how can we obtain a particle dynamics somehow that does this? And there have been kind of very interesting proposals in this community. So namely, Jose Antonio, Katie Craig, and Francesco Padaccini in 2019. They said, okay, if I want to have a deterministic evolution, right, that would approximate this heat equation, well, how about regularizing the relative entropy so that now this energy makes sense for particles? And okay, then I obtain these integral equations, and for this, an ODE system is an exact equation of this. And so I obtain a deterministic particle approximation for the Fokker-Planck equation. And there have been a number of results on this. In particular, Matt Jacobs talked about this, as I understand, on Tuesday, right? So there are, actually, the previous result by Jose Antonio, Katie, and Francesco, right? They did actually, the convergence was proved, right, for the entropies which were power laws, but not for the logarithmic one. But now using PD tools, they are able to show the convergence as epsilon goes to 0 of these dynamics towards the Fokker-Planck equation. Also, the question is, if we take epsilon to be positive, right, then the minimizer of this is no longer going to be pi. So basically, in terms of sampling, right, these schemes have a bias, and the question was how large the bias is, and let's say we have a small result on that, saying that the bias is actually going to be scaling like epsilon, and this in general is optimal, right? So, this is where things are right now. The problem is, again, the problem is that this is not viable somehow in high dimensions, and the reason is, okay, high dimensions are difficult, right? So if you want to have a good approximation, you need to take epsilon to be small. So your kernel has to be narrow, and then if you want to do, let's say, if I want to dealing with particles and I have a narrow kernel, to have any particles within the bandwidth of that kernel, right, I need exponentially many particles with respect to the dimension. So, okay, let's, so one needs kind of a different approach. I will, before I go on, right, before I go on to kind of somehow other possibilities, let me just mention something about the kind of what is the kind of promise and the hope of these interacting particle samplers. And for that, let me change the direction or the metric. So instead of a transportation-based metric, let me look at basically a weighted L2 type metric. So let me look at the Hellinger distance, or sometimes known as Fisher-Rao, in that case, right? Okay, so the metric is ut squared with rho, and the kind of the paths are given by this equation over here. The explicit form of the distance is this, and the explicit GD6 are known. If one interpolates in this way, the intermediate measures are not be two probability measures. The intermediate measures are not going to be probability measures. But if one restricts to basically geometric subspace of this to probability measures, then one obtains what is called a spherical Hellinger distance. And this has an explicit form in terms of the Hellinger distance, and the geodesics, again, are explicitly known. So this is a well understood metric, right? Now, if you look at the gradient flow with respect to this metric, right, then, okay, it takes this form, so it is a non-local equation, but there is no interaction really, right? You're just noticing at your location whether you have more or less mass than what you should, and you move mass where it needs to go. For these kind of flows, it is known in a large generality, right, that in this case, the convergence, exponential convergence holds, starting from, I would say, it doesn't have to be warm start, but at least not an entirely cold start. So you get exponential convergence with the rate that does not depend, even for multimodal distributions, on the height of the barrier, right? So basically, this bird-dead dynamics, it instantaneously sees if you have more mass in one well and less mass in the other well, and moves the mass non-locally from one well to the other, right? So if I want to have something like that included, right, just the ability to see how my mass is distributed globally, I need the interaction term, and this is really what all of the Monte Carlo Langevin approaches are lacking. And the promise of the interaction is to be able to include like bird-dead terms like this. Now, of course, if we're dealing with particles, we would need to regularize this, and I'm kind of resorting back to convolving with the kernel, just as in the previous approach. So again, this is problematic in high dimensions. But let's say for flows like this, now non-local evolutions like this, one can show that they converge as epsilon goes to 0, although under strong assumptions which should be improved. And even kind of parts of well-posedness theory, let's say we have this result where as epsilon goes to 0, the time of existence goes to infinity, but we don't have global existence for fixed epsilon. So anyways, there is a number of things that could be done, but of course the biggest problem is this also does not work in high dimensions. So just to be able to measure what my density is at my points so that I can decide whether I need to move stuff from one to the other, this is difficult to do in high dimensions. And I think this is kind of how to use the full power of interaction in high dimensions is really an interesting, somehow open question. Now, in terms of geometries, okay, so we saw that, okay, here, if I regularize the functional, right, then this is problematic in high dimensions. So how about instead of that, let me regularize the metric. Or use a more regular metric. So this was the idea by Liu and Wang. Again, people from computer science and machine learning community, right? They introduced what they call the Stein variational gradient descent. And what this is basically is that the metric of the flow is now the reproducing kernel Hilbert metric now in the vectorial sense. So basically, I'm penalizing the velocities much more heavily. I'm asking for the velocities to be very, very regular. And, but I'm not changing, or they are not changing the functional itself. So when one considers the Rayleigh functional and minimizes it, right? This is the flow that one obtains, and one could see that these velocities are very similar to ones that we saw in Fokker-Planck, but they're regularized by convolving with the kernel, or in this case, by convolving with the kernel K. Now, this flow does make sense on the level of particles. I can just plug in particles for rho, and I get this OD system, even though this OD system is not, there is no free lunch in some sense, because this OD system is no longer, it's not a discrete gradient flow, right? Before, my OD system was an exact gradient flow, but now the OD system is not a gradient flow. It is, however, a weak or a measure valid solution of this PDE. And this was, there is this beautiful paper by Lulu and Nolan from a couple of years ago where they exploit this and, they show the well-posedness for all of this and that the discrete ones are convergent to continuous ones on finite interval, on finite time intervals. And also they show convergence to the target measure, although this convergence is not exponential. So, let's compare, how these things work in practice kind of a little bit. So, here our target is a Gaussian. Why do I use a Gaussian target? Because then I can tell you explicitly what those integrals in MMD towards a Gaussian can be explicitly computed, so I can measure the distance to the target measure very precisely. So if the way that I measure the error is the maximum mean discrepancy, and I do the gradient flow of the maximum mean discrepancy, actually gradient flows are too slow to converge, so this is a quasi-Newton scheme. Well, of course, they give the best results, right? That is not somehow surprising. But I will note that these other schemes, this Stein variational gradient descent and some variants thereof, are all actually giving an error which is quite a bit better. You see this black line at the top are the perfect IID points of the sampling. So this is actually the best that one could expect if one was using any of the Monte Carlo, let's say, sampling algorithms, right? So these are the IID points, and these output of the interacting particle samplers is giving us kind of a better quantizations of the measures that we are considering. Okay, so if I look at the error rates, as I said, the power is going to be bigger than -1. Those theoretical results suggested that the error is at least as good as -1, but we see that the error is actually consistently below -1. And again, there is no guarantee that these algorithms are reaching actually the minimum, right? This is open. But then, we look at the samples that one is obtaining, right? So this is, this is the true IID points. This is the one thing that we introduced. So this is the normalized Stein variation gradient descent. Here it gives a very regular pattern of points. But if I look at this MMD, right, and the one that gave the best result, I have to admit, I chose a particularly disadvantageous example of them. Many times their result will look something like this, but I chose, it's not too rare that something like this will happen. So, indeed, right, this is the minimizer, it gives the best result. And I think that this is somehow, even though on the continuum level, the minimizer is the smooth distribution, I think at a discrete level, there is still some trace of the singularities that smooth interaction potentials like. There is absolutely no understanding of patterns that show up in, discrete minimizations of maximum mean discrepancy. So, but then you will say, well, how can this be that this is the best sample? Well, you see the bandwidth of these patterns is slightly less than 1, right? And the kernel width that was used to design this is 1, right? So basically, since the functions, k determines the smoothness of the functions that you will be integrating, there may be patterns below that length scale, right, that do appear. And here is a stress test of that. So here we looked at the same output of the algorithm, which is obtained by using MMD with bandwidth 1, and but we change the bandwidth of the evaluation metric. So here I evaluate with the same metric that this was minimizing, and of course this gives the best result. But now I choose a slightly narrower kernel for evaluating, let's say 0.7, then there is no difference. And if I take 0.3, so something considerably smaller than those length scales, then we see that this MMD is actually a little bit kind of random, but no better than the IID sample, whereas these other ones that kind of seem to have a nice pattern, right? So would be successful in the eyeball norm, they tend to be robust kind of in terms of changing the how we measure it, right? Okay, so SVGD then seems to be kind of maybe a good tool to use, but SVGD has problems on its own. So namely, right, if you, again, the problem with SVGD is that there is a convolution over here, and as we saw, convolutions are, even though here there is no requirement, so unlike the blob regularization, for SVGD you can take K to be as wide as you like, it will still converge. But if you take a larger K, then the exponential convergence becomes incredibly, it's not going to be exponential, but I meant is the convergence is becoming very, 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 very slow, right? And okay, I can discuss that kind of at length at the level of linearization, and somehow they do, you know, you cannot use very wide kernels. If you look at somewhat narrower kernels, then they cannot be approximated well in high dimensions. There are papers on this, or there is a paper by Erdoglu's group on, you know, collapse of variance in SVGD. So even for a Gaussian target in high dimensions, they do not work very well. So okay, so what is a better maybe than thing to do? What proposal would we have? Well, let me introduce, you know, quickly Radon transform. So Radon transform of function is, you know, so we have a function in RD, and then Radon transform will depend on an angle and a one-dimensional variable p. Okay, so first we pick an angle theta, all right, so basically unit vector theta, right? And then I look at the projection to that, so orthogonal projection to that line segment, and then to obtain what is the value of the Radon transform at this point, p, in the theta direction, I just integrate the function f along the orthogonal hyperplane to the direction theta at that point. Or in other words, right, so one could, you know, well, okay, here is really that formula, right, and, right, you know, well, okay, yeah, let me not go into, so slice-Wasserstein distance is quite interesting, and we spent quite a bit of time studying it. I will mention, yeah, okay, I'll skip this as well. Okay, so here is the somehow the proposal that we have. Okay, by the way, I just need one more object, sorry. Right, so here I introduce the Radon transform. Now, this R star is the dual of the Radon transform, and dual of Radon transform is now, okay, so, you know, X is in the RD, but the theta and X dot theta needs to be in SD minus 1, and X dot theta is in R. So you integrate the function g over a ball, basically, to obtain the dual Radon transform, and right, it satisfies, you know, kind of the classical, you know, kind of duality result. Radon transform, I should note that, okay, maybe just one other thing, right, is Radon transform is a regularized, you know, you're integrating over the d minus 1 dimensional objects, so you're making the function smoother as you are evaluating the Radon transform, and in fact, right, it is anisometric. Let's just look at this thing here. It is an isometry between, let's say, it increases your regularity if you're looking at the fractional subbolus spaces, basically by d minus 1 over 2. Okay, one needs to look at these attenuated subbolus spaces, but the moral is that this is how much it increases the regularity of your functions. Okay, so to introduce kind of my proposal gradient flows, the basic idea somehow is the following, right? Is if you want something that can be approximated in high dimensions, basically the class of velocity that you're considering needs to be simple enough that it kind of has a low VC dimension that can be approximated well in high dimensions. So there is this kind of computational complexity behind it. So, okay, what are the simplest velocities I could think of? Well, maybe the velocities that only change things in one dimension. So basically I choose the direction theta, and then I only allow velocities that basically move the whole hyperplanes by this one-dimensional velocity given by u. If I look at, you know, in this way, we get a semi-metric that only allows motion in direction theta. But now let me look at the metric that I obtain by looking at velocities that I can decompose in this one-dimensional velocities studied over there. And then the metric is the inf convolution of these metrics over here. In terms of the Radon transform, right, this could be actually defined as the following, right, is that V is actually a dual Radon transform of W, and what we're paying is this integral of these g thetas for each W. in this sense, okay, one obtains, I know that I'm kind of running out of time, but let me just make the proposal. So in this way, okay, let's look at the relative entropy, and let's look at the gradient flow in the metric that I just wrote out. Well, this would actually be, if you're looking at an inf convolution of metrics, then the gradient flow of the inf convolution is the integral or the average of the gradient flows with respect to each individual metric, which in this case has the following form. So R is the Radon transform, R star is its dual, and the wonderful thing that that happens here, it's kind of a little miracle, is that the equation closes really at the level of the projection. So basically the diffusion term does not require really a convolution. It only requires computing the Radon transform, then the logarithm, and then we compute the gradient. Now, so if I need to approximate this for particles, right, then okay, okay, Radon transform is easy to compute, but then I need the density of the Radon transform. But once I have the projection to one dimension, in 1D, right, kernel density estimation works very well, and I can approximate the density of the Radon transform very well for any of these projections. So basically, you can take K, which is a pretty narrow kernel, and you obtain this flow at the level of the projections. So again, you know, all of this can be approximated well in high dimensions. And when you want to do it in high dimensions, you pick a random angle at each time. But then this is like a Monte Carlo integration over the sphere. So basically what you know, the error that you obtain is like 1/4 root of n. And well, what this does is it works, you know, faster than SVGD in terms of convergence. So each, you know, the advantage here is that each step is incredibly fast. You do need kind of more steps, but each step is incredibly fast. I don't have time to kind of go into this. And the other thing that, unlike SVGD, this actually applies in high dimensions. So basically, okay, what we, you know, presented in the end here is a flow that can be used, you know, it's a deterministic interacting particle gradient flow. It has a gradient flow structure, and it can be approximated well in high dimensions. Does this solve the multimodal distributions problem? It does not, right? But then one hopes to be able to now use the interaction. At least kind of this first part in this sense is done. Well done in a very weak sense, because I have been giving this talk for a year now, and I always say, well, the existence for this is in progress. I don't have, we don't have the proof of the full proof of it. There is stability, we have some stability results, but we don't. And my student is graduating, so if you want to collaborate, I can, you know, buy a wine at the dinner or something, right? So, yeah, anyways, I think this is a good time to stop. Thanks.
Okay, thank you for the nice talk. Dejan, questions, comments? Yeah.
Because you are talking about the measure valued solution, but in fact, I think you mean just a solution in the space of measure, yes?
Yeah.
Not like Diperna.
Right. Yeah, no,
measure.
Right. I know that there is, right.
Okay, thank you.
But, yeah.
More comments, questions?
Still speaking about the well-posedness, I mean, you mentioned stability estimate, that you have some stability estimates, but in...
Well, okay, that's somehow an overstatement. What I have is that, let's say, if I have a sequence of solutions of just this part of the equation, so basically this would be the heat flow in this sense, right? So you see that this is no local interaction is hidden in Radon, but then this logarithmic nonlinearity is the troublesome term. So if I have a sequence of solutions, right, then I can show compactness, and that along the subsequence they converge to a solution. So it's just that, right?
Okay. Thank you.
Thanks for the really nice talk. Could you just explain a little more how the computation of this works, how it's ON?
Yeah. Thanks. Well, where did I go? Right. So, okay, so, right, this is an OD, right, so, right, okay, let's say the true, right, so at the OD, you know, you can say particle level, right? So if I wanted to compute how a particle goes, right, I would need to compute this integral over all possible angles. What we actually do is you fix an angle at a time step, right? And then for that fixed angle, so there is no integral, right? You are just doing this. So this is, in a sense, is SGD, so stochastic gradient descent for this functional over here. And that part actually is in the T. So Lantiano was able to show that at least that part on the OD level, it does work, right? That you can take, you know, this is very standard, just using the standard SGD techniques. But, you know, in terms of computation, one thing to note that since I only need, you see, this is K is a one-dimensional kernel, right? And I really need to interact, you know, the points which are interacting are the projections of these points. So basically, you can sort them, right, which is n log n. And then you can take actually a rather narrow kernel, right? So basically, the complexity of each step is, you know, certainly less than n squared, right? So it is, you know, because in higher D, just computing the matrix of pairwise distances and realizing who your neighbors are is of complexity n squared. And, you know, that is kind of one limitation of here compared to Langevin. But on the other hand, for this Radon guy, you don't have that limitation here. So basically, complexity, if each step is, I would say, n plus, you know, a little bit worse than n. Okay, the number of steps, you know, the sampling of these angles, even in high dimensions, is not really problematic, right?
Thanks.
Any more questions, comments? Okay.
No, I just had a comment. So I had the idea, so in general, if you want to speed up convergence, wouldn't you want to put a mixing flow into these particles? So something that doesn't change your base measure, but it like mixes, so
Right.
some exponential mixer or something like that.
Right. So, so Gautam is my colleague, right? And he's also interested in sampling. Gautam is, you know, kind of one of the, Gautam Iyer, right?
Yeah, yeah.
He's one of the experts somehow in mixing. So we considered various things somehow about mixing, right? But nothing really that makes so much sense in somehow high dimensions. So let's say, when thinking about mixing, I would say, you know, think about the two-well thing and think about what would effectively mix somehow between two wells. What we actually see more hope in, you know, to be honest with you, we're working on our now proving rigorously convergence for tempering strategies, so, or quenching, if you like, right? So, right, in terms of kind of overcoming, yeah, that part is, yeah, this is what we are looking at. Also, I would say, you know, there are interesting open directions in kinetic Monte Carlo, right? So, right, yeah, and we can discuss that, right? So, in terms of using the flow, right?
So I think we should postpone the questions to the coffee break. Let's thank David again.